So in this video, we're going to take what we learned in the last video about RC circuits and actually do a couple of examples solving for RC circuits. Let's take this RC circuit, for example, where you have a resistance of 150 ohms and a capacitance of 72 microfarads. The question is, first of all, what is the time constant of this circuit? By the way, 72 microfarads is kind of on the upper range of what capacitances are, but that's okay. You'll often deal with nanofarads, sometimes even picofarads in homework. All right, back to the question, what is the time constant of the circuit? Well, time constant, remember, is just resistance times capacitance. So that's 150 ohms times 72 times 10 to the minus 6 farads. Remember, micro is 10 to the minus 6th. There we go. And that comes out to 0.0108. Time constant is in seconds. Now that is 10.8 milliseconds. So it's a very quick time constant. What this basically means is it takes 10.8 milliseconds to reach 63% of capacity. Okay. So using that time constant, let's ask our next question. What voltage will the capacitor hold after 30 milliseconds? Now, for this, we need to know what the EMF is. I'm just going to tell you, we're assuming that this is hooked up to a 12-volt battery. It could be anything, really. All right? So the voltage of the capacitor is going to be your EMF times 1 minus e to the negative t over RC. So that'll be 12 volts for your EMF minus negative e to the minus 30.0 milliseconds divided by 10.8 milliseconds. An important thing here to note is that these two have to be the same unit. This math will not work if they're not the same unit. So double check that always. All right, and so when we do this, we get 12.0 volts times 1 minus e to the negative 30 divided by 10.8, 2.778. All right. So when I plug that in, I get 12 volts times 0.9378, which means that my capacitor is charged to 11.254 volts. So not quite up to its fullest capacity, but pretty close. You need to give it a fair amount of time. Of course, if you let this go on indefinitely, then your capacitor would eventually reach 12 volts. All right, so now here's a different type of question. How much time is needed to reach 50% of capacity? Again, your capacity is 12 volts. We want to know how much time is needed. Now, in this case, we're going to have to actually solve for time. So that's pretty easy to do. VC over the EMF is going to equal 1 minus e to the negative t over RC. So e to the negative t over RC would equal 1 minus VC over the EMF. Now here's where it gets tricky. How do you solve for time when it is an exponential? It is in the exponent. Remember from algebra that if you have some number to the x and that equals y, then we can take the inverse function to resolve that. Remember, an inverse function would be, say, x squared equals y. Well, how do you get rid of the square? Well, take the square root. So the square root is the inverse function of the square. So we need to do some sort of an inverse function for this exponent, and that exponent is going to, or that inverse function is going to be the logarithm. In this case, the base number a is e, so log base e of y, which we also call the natural log. So in order to find the value x, we need to take the natural log of y. Okay, so that means x, which is the exponent, negative t over rc, is going to equal the natural log of 1 minus vc over EMF. So the time is going to be negative rc natural log of 1 minus vc over EMF. All right, plug that in. Negative rc, that's my time constant, 10.8 milliseconds, times the natural log of 1 minus voltage of my capacitance. Well, that's half. That's half of the total capacity, so that's 0.5 times the EMF divided by the EMF itself, which cancels. That means your time is negative 10.8 milliseconds times the natural log of 1/2. Natural log of 1/2, you just plug that into your calculator. Let me double check that. Oh, I knew I'd pushed the wrong button. Okay, negative 0.6931, somewhere around there. So if I multiply that by negative 10.8 milliseconds, whoops, times negative 10.8 milliseconds gives you 7.486 milliseconds. So it takes right around 7.5 milliseconds to reach 6 volts, half of its capacity. All right, next question. We're moving to a discharging RC circuit. We've removed the EMF. We want to know how much charge remains in the capacitor after 15 milliseconds. Well, we need to know how much charge is in there. Remember that Q equals CV. So let's assume that this is a fully charged capacitor. 72 microfarads times, it was at 12 volts earlier. 72 times 10 to the minus 6 times 12. That'd be 864 microcoulombs. All right, so your initial charge is 864 microcoulombs. We're just assuming the capacitor had enough time in this setup to fully charge. Okay, that's beside the point. That was just to give us a number. Now we want to know how much charge remains after 15 milliseconds. Well, remember that the discharging equation for both charge and voltage is your initial value times e to the negative t over RC. So that's going to be 864 microcoulombs times e to the negative 15 milliseconds divided by 10.8 milliseconds. Again, you have to have the same unit in there. So that's 864 microcoulombs times negative 15 divided by 10.8, and then take e to the power of that, 0.24935-ish. So basically, after 15 milliseconds, you have a quarter of the initial charge that you had, a quarter being 0.25. So if I multiply that by 864, I get 215.4 microcoulombs, and that's how much charge is on the capacitor after 15 milliseconds.